Hello, my name is Ben Douglas. I'm an undergrad at the University of Colorado Boulder, and for a few summers I have worked with my mentor Catherine Elder at the NASA Jet Propulsion Laboratory at Caltech. And the project that I'm going to be presenting is constraining the thickness of the lunar regolith using cold spot craters. As many of you know, regolith is made up of fine-grained particles broken up by impacts over billions of years. So why do we care about regolith? The moon is mostly covered in regolith, and its formation is the dominant geologic process on the moon and has been for billions of years. So to understand the geologic history of the moon, we need to understand the regolith. Additionally, regolith is abundant on many airless bodies, so it's relevant to the study of many worlds throughout the solar system. Here on the map of the moon, I have marked the two regions that I'm looking at, Oceanus Procellarum on the left and Mare Tranquillitatis on the right. So before I get into my research, I'm going to talk about a study by Wilcox et al. 2005. This study worked on constraining the thickness of the regolith layer of the Mare regions of the moon. They used multiple methods to do this, but the method I'm going to be focusing on is the blocky craters method. The way that this method works is it looks at how many blocks there are around fresh-looking craters, and if there are no rocks, like in case B here in the figure, the impact did not excavate blocks from below the regolith. However, if, like in case A in the figure, there are blocks present around the fresh crater, then the impact did excavate blocks from below the regolith. So this study looked at lunar orbiter images in the regions I showed in the previous slide, Oceanus Procellarum and Mare Tranquillitatis. Here are the results of the Wilcox et al. 2005 study. Taking a look at the figure, the x-axis is crater diameter split into 50-meter bins. They range from 75 to 125 meters, 125 to 175 meters, etc. The y-axis indicates the percent of craters that either have no blocks, which is white, one to a few blocks, which is gray, or more than a few blocks surrounding the crater, which is black. So the reason for the middle category, the one to a few blocks in gray on the graph, is to account for the possibility that a rock may have been mixed in with the regolith or may have already been present on the surface nearby, and so it wasn't excavated. So the one to a few blocks category is figuratively and literally a gray area. And as you can see in the graph, the smallest diameter bin from 75 to 125 meters in diameter consists mostly of craters with no excavated blocks in the surrounding regolith. And as diameter increases, the percent of blocky craters also increases. All the craters with a diameter larger than 525 meters have at least one block in their surrounding regolith. A potential problem with this method is that blocks on the moon's surface break down over time due to impacts. Studies in the last decade using lunar reconnaissance orbiter data found blocks break down faster than previously thought. Now here what we are introducing to this research method is a new class of craters called cold spot craters, which some of you are probably familiar with. The key characteristic of cold spot craters is that they are less than 1,000,000 years old, whereas blocks 2 to 3 meters in diameter break down in around 100 million years, which is faster than previously thought. This means that if we do not see blocks around a cold spot crater, we can be relatively certain that the impact did not excavate blocks in the first place, because they would not have had enough time to break down. Our overall project goal is to use block populations surrounding cold spot craters to constrain the thickness of the lunar regolith, and we're looking for regional differences in regolith thickness as well. We're also comparing our results to the Wilcox et al. 2005 study to assess the effects of crater age on regolith depth estimations based on crater ejective blockiness. First, we had to figure out which cold spot craters to use for comparison with the Wilcox et al. 2005 study. This figure from Hiesinger et al. 2011 shows a map of the lunar maria and the geologic units they identified and dated. The color of the geologic units indicates its age, in accordance with the color bar on the right. We overlaid it with a map of all the cold spot craters on the Moon, which are the cyan dots. Now, if we zoom into these regions in Mare Tranquillitatis and Oceanus Procellarum, you can see we also plotted the image bounds of the lunar orbiter images used by the Wilcox et al. 2005 study. In each of the two regions, these images lie in the same or similarly aged geologic units. We know that older surfaces are expected to have developed a thicker layer of regolith. Because of this, we want to look at cold spot craters in either the same geologic units or nearby geologic units of similar age. In Oceanus Procellarum, we looked at cold spot craters in geologic units in an age range of 1.9 to 3.1 billion years old. And we used all the cold spot craters in Mare Tranquillitatis, since the whole region ranges in age only from 3.4 to 4.2 billion years old. This method, using cold spot craters from nearby geologic units of relatively similar ages, allows us to increase our dataset of cold spot craters. Once we had selected our cold spot craters, we found the best image of each cold spot crater from the Lunar Reconnaissance Orbiter, and we used ArcGIS to record the number of blocks around each crater. We binned each crater as having 0, 1 to 3, or 4 plus blocks in the surrounding regolith. There were a few limitations we had to make to be able to consistently see blocks and make fair comparisons between craters. First, we had to reduce the image resolution to 1.5 meters per pixel for each image. All the images we had ranged in image resolution from 0.5 to 1.5 meters per pixel. To be able to make fair comparisons between the images, they had to have the same image resolution, or else we'd be recording blocks and images with 0.5 meters per pixel, despite not being able to see the same size block in a 1.5 meter per pixel resolution image. We also limited the incidence angle to between 25 and 80 degrees to consistently be able to see blocks in the images. We did this because in low incidence angle images, there was almost no shadow from the block and often very high albedo, so we couldn't consistently see blocks. On the other hand, at high incidence angles, the shadow from the crater rim covered part of the ejecta blanket surrounding the crater, which made it impossible to see all the regions that could have blocks. Lastly, we only counted blocks within 1 crater radius of the crater rim. We did this to ensure that the blocks we counted were likely excavated by the impact, rather than counting a possible stray block on the surface from a different impact. These constraints represent a balance between maximizing the number of cold spot craters we're able to include and minimizing the difference in block detectability between the images. Here are the Wilcox et al. 2005 results from earlier on the left versus our results on the right. Again, each graph has 50-meter diameter bins, with the first ranging from 75 to 125 meters. In our graph, craters with no blocks are in yellow, craters with 1 to 3 blocks are in red, and craters with 4 plus blocks are in blue. The first bin in our result is only about 2/3 craters with no blocks, whereas for the Wilcox et al. 2005 results, the same first bin is about 90% craters with no blocks. The percent of craters with no blocks decreases more quickly as diameter increases for our results than the Wilcox et al. 2005 results. In fact, by the second bin ranging from 125 to 175 meters in diameter, less than 20% of our craters have 0 blocks, whereas the Wilcox et al. 2005 results show 80% of craters in the same second bin having no blocks. The largest crater with no blocks in our results is in the 225 to 275 meter bin, whereas the largest crater with no blocks in the Wilcox et al. 2005 study is in the 475 to 525 meter bin. These are notable differences between our results, with our results indicating thinner regolith than the Wilcox et al. 2005 results. We think these differences are likely due to the differences in the ages of the craters we considered. Next, let's take a look at the two regions separately, Oceanus Procellarum and Mare Tranquillitatis. Here, the Wilcox et al. 2005 results are on the left, and our results are on the right. And in addition, the Oceanus Procellarum results are on top, and the Mare Tranquillitatis results are below. We estimated the maximum regolith thickness in each region by using a scaling law from Pike 1974. This involves multiplying the crater diameter of the largest crater that did not excavate blocks by 0.1 to get the maximum excavation depth. We chose this scaling law to be consistent with the Wilcox et al. 2005 study. After applying this scaling law, the Wilcox et al. 2005 results show that in Oceanus Procellarum, the maximum regolith thickness is 32.5 meters. And in Mare Tranquillitatis, the maximum regolith thickness is 47.5 meters. On the other hand, our results show thinner regolith in both regions. We found that in Oceanus Procellarum, the maximum regolith thickness is 17.5 meters, and in Mare Tranquillitatis, the maximum regolith thickness is 27.5 meters. Both of our studies find thinner regolith in Oceanus Procellarum than Mare Tranquillitatis. This makes sense because older surfaces have had more time for regolith to develop, so they may be expected to have a thicker layer of regolith, and Mare Tranquillitatis is older by about 1 billion years. In our first bin, which includes craters with diameters between 75 to 125 meters, about half of Oceanus Procellarum's craters have no blocks, whereas about 2/3 of the craters in the first bin of Mare Tranquillitatis have no blocks. Additionally, in Oceanus Procellarum, the largest crater with no blocks is in the 125 to 175 meter bin, and in Mare Tranquillitatis, the largest crater with no blocks is in the 225 to 275 meter bin. However, our study is limited by the number of cold spot craters and the availability of suitable images. We were only able to consider approximately 40 craters in each of the two regions used for comparison to Wilcox et al. 2005. So we can't draw any strong conclusions about differences between these two regions. Returning back to the combined graphs, it is clear that we have differences in our results, with our graph indicating thinner regolith than the Wilcox et al. 2005 study constrained. This is likely due to our use of cold spot craters, which were discovered after 2005. That ensured craters with no blocks present in their ejecta really didn't excavate blocks during the impact, since not enough time passed for blocks to break down. It's possible that some of the craters Wilcox et al. 2005 looked at were old enough for smaller blocks to have broken down, which makes them appear as if they did not excavate blocks. This suggests that using young craters, such as cold spot craters, is critical when using block abundance in crater ejecta to estimate regolith thickness. In conclusion, we found that the majority of craters excavate blocks in the lunar maria. We also found that previous work that included older craters may have found block-free craters because the blocks had already broken down. Additionally, there is a possible difference between the regolith depth of Mare Tranquillitatis and Oceanus Procellarum. We will be continuing this research in more regions of the lunar maria to get more widespread constraints of the thickness of the lunar regolith. Thank you for listening to my presentation, and I'm looking forward to giving my lightning talk and answering any questions.